Good morning, good afternoon, or good evening, depending on where you are in the world, and welcome to today's DevOps.com program, brought to you by TechStrong and ScyllaDB. My name is Cody J. Brown. I'm the host of TechStrong Learning, and we have an exciting program for you ahead. First, I do have just a couple of housekeeping notes. Today's session is being recorded. If you miss any of our discussion, or you'd like to rewatch or share with a friend, the on-demand recording will be made available shortly after we conclude our live session today. If you have any questions, we want you to send those in to us using the chat tab, for questions, we want you to send those in using the Q&A tab, which you'll find on the right side of your screen. And then you'll also find that chat tab where we want you to let us know from where you're from or any thoughts that you have throughout today's program. We do have a couple of polls for you throughout today's webinar, so we do want your participation there. And there's a copy of the slides available for handout if you click the Handouts tab. Of course, before we close, we are also giving away 4 $25 Amazon gift cards, so be sure to stick around. So the topic of our program today is transforming the database, critical innovations for performance at scale. And I'm joined by Zach Livyatan, VP of Product at ScyllaDB, and Benny Halevi, Director of Software Engineering at ScyllaDB. Benny, Zach, thank you both so much for joining me. I'd like to turn the program over to Zach to get us kicked off.
Thanks, Cody. And hi, everyone. Good morning, good evening, depending where you are on the globe. The session today will be transforming the database, critical innovation for performance at scale. As you will see, Scylla is all about performance. So we have a lot of performance features that we could pick from. We try to pick selected, I would say, a number of features. Some of them are more essential, some of them are more new, and I hope you will enjoy the session. Please do ask questions throughout the presentation. We will try to answer a few during the session, and what we cannot answer during, we'll answer at the end. I do want to mention a very relevant and related conference, P99 conference, a full, very technical conference just about performance, in particular low latency, as the name might suggest, with presenters from Scylla and many other companies. So please check it out. I'm sure it would be interesting for you. Before we get started, a quick poll. Where are you in your NoSQL adoption? So we'll let everyone to answer. Okay, and let's get going. As Cody mentioned, I'm Zach Livyatan, VP Product at ScyllaDB. Before that, I spent time at Oracle, and even before that, spent some time in the telecom domain. Benny, I will let you introduce yourself.
Hi, so I'm Benny Halevi. I manage the storage team in Scylla the last 4 years or so. I've been doing a lot of operating systems and file systems work along my career. Now I'm applying it in the NoSQL databases business. Thank you.
Thanks, Benny. So Benny and I will switch each other on each section of the agenda. First, I'm going to briefly introduce Scylla, the company, and Scylla, the database. Then I'm going to take you in an historic session of a few minutes as an introduction to the Scylla architecture. Benny going to explain the latest and greatest I/O scheduler, and switch back to me to explain how this I/O scheduler, together with latest instance for Amazon, brings Scylla to a new level of performance. Switching back to Benny to present one of our latest benchmark of a petabyte database or experiment. And then, if time permits, I'm going to cover a few additional performance improvement in the latest release. I'm not sure we'll get to it, to be honest. At the end, we will try to keep 10 minutes for Q&A. So ScyllaDB, or Scylla, is a NoSQL database that was built from scratch for performance. We'll talk more about that. And when I'm saying performance, it's actually two different but related parameters. One is throughput, how many requests per second each instance or the entire cluster can handle. The second one, which is also very important, is latency. In most workloads, Scylla keep a latency of lower than a millisecond on average, and the P99 usually less than 5 milliseconds. Scylla come in 3 variants. One is the open source. You can go to GitHub, download the code, compile it if you have a few hours, look into it, send a PR. The second one is enterprise. It's a closed source project, very much based on the open source. 90-something% is the same base of code, but it do have some extra feature, some around security like encryption at rest, some around performance. And last but not least, Scylla Cloud. Scylla Cloud is a database as an offering service which runs Scylla Enterprise. So it's the same database, and the main difference is that we manage database for you, either on AWS or GCP. And recently, this seems like a very attractive offering. Most people don't like to manage their own software these days. And that's true probably not just for databases. Okay, some of our users and customers, as you can see, they are coming from many different domains. I would say that the common between all of our users is that they are looking for a combination of high availability and performance. And I will explain. In this session, we'll be focused on performance, but high availability is another very important aspect of Scylla that is mostly out of scope of this session. And this is the only slide I dedicate to high availability, just to show that the architecture of Scylla. So Scylla can run in a multi-region or multi-data center, as sometimes we call it, deployment. It uses eventual consistency, and you can actually use tunable consistency both for read and write. You can read and write in quorum or in one or in all consistency, and this is a typical deployment. In this session, after this slide, we're not going to talk about high availability at all. Instead, we're going to zoom in into one of the data center and one of the node in the data center and explain how we made this node perform as much as fast as possible. But if we zoom out, we'll see it's actually part of a bigger cluster, and it's very interesting, just not part of this session. So with that, I will switch to the quick history lesson I promised earlier. In the last, and I promise it will be short, in the last 20 years or so, hardware significantly changed. So if we look at the changes in CPU, memory, networking, storage, everything changed. Let's start with the CPU. So I'm sure everyone here is familiar with the Moore law, that number of transistor per CPU increase, and that's continuing to be true for now. But if you look at the speed of the CPU in the last 10 years or so, it's actually flattened. What continued to increase is the number of core per machine. So if you are old enough like me and Benny here, sorry Benny, you know that 10 or 15 years ago, a 2-core laptop considered to be very, very strong, or even a production server used to be strong with 4 cores. Now, every laptop have at least 4 cores, and production server have 64 core, 96 core, and it's only increasing. So that's a huge change in architecture. And spoiler alert, I will show how Scylla was built to handle this change. Other changes include, for example, NUMA, which basically means that the memory is not evenly distributed between the CPU. Rather, its chunk of memory of RAM is physically closer to one of the CPUs. So it's preferable to this CPU to work with this part of the memory. And there are other changes in storage, in RAM. Storage, of course, become much faster with SSDs. And Scylla was created to and optimized to work with these SSDs. Benny going to talk a little bit more about it in his I/O scheduler section. A network card was improved. Everything was improved. But some of the application that was created in the first wave of NoSQL database, Apache Cassandra is one example, was not built with this new hardware in mind. So if, of course, database exists for decades, And for many years, a relational database was everything that we needed. But at some point, with what used to be called internet scale, one server was simply not enough to hold all the information, and we have to move to a NoSQL model when data is distributed between many servers or partitioned between many servers. The first wave or the first generation of NoSQL database fixed this problem or tried to solve this problem, and databases like Apache Cassandra did it in a pretty efficient way by implementing partition algorithm and eventual consistency. And that's worked fine. But in the process, because it was built 15 years ago or so, they didn't take into account all the new hardware that was introduced in there. And Scylla had the benefit of using both the algorithm that came from Apache Cassandra and the Dynamo paper, but also take into account latest hardware. And we'll see how that improves our performance. That's another way to look at the NoSQL domain. Of course, NoSQL, just for people who are not familiar with it, it's a huge domain. There are many databases. Each of them have a slightly different properties. Some call new SQL, some NoSQL. For those of you who are not familiar, Scylla is categories, sometimes called wide partition, wide row. It's similar in data modeling to DynamoDB, Apache Cassandra, HBase, and other databases. It does not support a full SQL relational database. It supports a subset of that was built for high performance that called SQL or Cassandra Query Language. So the first, and I think that's the most important performance concept that was implemented in Scylla right from the start, is shard per core. And if you remember just a few slides away, I remind you that modern hardware have many core per machine, sometimes 24, 64, 96. And Scylla was built from scratch, assuming huge or big number of core per machine. Traditional application like Apache Cassandra and other was built on a concept of many threads. You spawn as many threads as you basically can, and these threads are competing for resources. And this is actually something that when 10 years ago we started to profile in Apache Cassandra and other application, mostly Java application, but not just, we've seen that a huge percentage of the actual compute time is spent on this thread competing with each other, waiting for each other, context switching, and such. And actually, you don't use the benefit of your CPU because all of these threads are just fighting for each other, either synchronizing for a memory, synchronizing for a disk, waiting for each other to do blocking action. And the main principle that was implemented in C-Star, a library I will talk about in a second, and in Scylla, is a shard per core architecture. Shard per core is, if you want, a development paradigm that limits the threads to the number of cores. There is one thread per core. All action on this thread is completely asynchronic. Because there is only one thread, it can never be blocked. So as a developer, you have the responsibility to never block this thread. And this thread is never context switch. So all of the overhead that come with multiple context switches completely disappeared. And that's, of course, bring huge improvement in performance. This principle actually take advantage of partitioning. So if you work with a NoSQL database or even SQL database like MySQL, you are probably familiar with the partition concept. You take the data and partition it to chunks based on some partition key. Each node handle part of or partition of the data. In Scylla, we took this principle one step further. We are not splitting the data just per node. We are also splitting the data per partition, per core, sorry. So each core on the machine actually handle a chunk of the data and is allocated with a chunk of memory, chunk of disk, chunk of network queue. We try to split all the resources between the cores so they don't have to fight each other. They don't have to fight for the same resources. And as a result, work much faster. And this is a diagram that tries to capture that. In the left, you see a traditional application with many threads. Each of them is competing for memory, networking, storage, and doing all kind of, each thread can do at any point a blocking action, like doing a block read from or write to disk, and then another thread will context switch and start running. This works fine as long as you don't need high performance. When you do need high performance, you want to eliminate all of this context switch, and that's exactly what the CStar library do. CStar is a C++, open source, of course, C++ library that implement this shard per core architecture. Every thread run on a specific core. There is no shared memory at all between the cores and the threads. If two threads or two cores need to share information, they use message queue. Each core is allocated with the network queue if possible. Not always you have enough. So each core run independently. And this actually proved to bring huge performance improvement. And the CStar library is becoming more and more popular with other open source applications that look for high performance. You can look at Red Panda, for example, which is a Kafka replacement, Value Store, and many other. So if you're interested in high performance architecture, maybe you can take CStar and at least learn from it. And with that, I'm going to soon switch to Benny to explain a little bit. By the way, this decision, this shard per core architecture was, I think, the first design concept that we have in Scylla and CStar in general. And what Benny going to show is some of the latest work that we did, because we are always keep to pushing performance further and further. So with that, we'll switch to Benny to explain our latest IO scheduler.
Thank you, Tzach. So to present the Scylla IO scheduler, we need to understand why we need scheduling at all. So in Scylla, we have different software components that all compete for limited resources. And one of these resources is the disk. These different components have different priorities, and they don't have a good way to coordinate with each other and to throttle themselves to not overconsume the shared resource. So in Scylla, we came up with a concept called the scheduling group. And currently on the IO front, it's called the IO priority class, which is the same thing. And in the center of this diagram, you can see a few of the consumers for the disk resource. We have the commit log writer that writes to files in place, usually in fairly small IOs. We have the memtable flush process that flushes the dirty data out of the memtables onto persistent SS tables. And in parallel to those, we have the compaction process that's doing both reads and writes. And we have the regular query IO that's triggered by SQL queries. So to manage the different priorities between those processes, we associate each process with a scheduling group. So you can see that commit log and memtable both use a shared scheduling group called here flush scheduling group. Compaction has its own scheduling group, and the query has the query scheduling group, which is the default scheduling group. Now, at any given point in time, each scheduling group has a number of associated shares, so that the priority is determined by the relative ratio of shares between different IO requests that are scheduled in the queue. So to tweak the number of shares in real time, on the left side, we can see that we have several monitors in the system. So for example, the memory monitor on the upper left corner is continuously measuring how much free memory we have in our memory pools. And as we run out of free memory, we know that we would like to increase the priority of memtable flushing. So in this case, it will assign more shares to the flush scheduling group, allowing memtable to consume more I/O. In parallel to that, we have the compaction backlog monitor. So as more and more SS tables accumulate, and if when you have too many SS tables, this may reduce performance because you need to read more files to get the contents of a particular partition. So when we measure that the backlog increased, we increased the number of shares assigned to the compaction schedule group, etc. Now, other than increasing shares, we also want to control how many IOs we send in parallel to the disk. The disk is a finite resource. You can't just send an infinite number of IO requests to the disk, and they can't all be performed in parallel. So as we can see, the basic model for the disks show that as you increase the concurrency on the x-axis, we see two things happening. First, the blue line shows the throughput, how many IOPS we can effectively get from the disk. So as you send more concurrent requests to the disk, we do get a higher throughput, up to a point where throughput is saturated. But at the same time, each IO request is served in higher latency. And even when we get to saturation, sending more requests doesn't help. It just increases the average latency. One more thing to note is once a request is sent to the disk, you can no longer affect its priority. It's scheduled to be executed either for read and write. It can't be aborted. And you can no longer reorder the queue. So we have a challenge how to balance the concurrency, how many requests we send to the disk, versus the number of requests that we keep in software queues, where the advantages of keeping requests in the software queue is that we can first cancel them, say if they time out, and also we can reorder them based on the shares mechanism I described earlier. So what we learned over time is that this simplistic model is not enough to prevent saturation for the disk. This looks similar for reads and writes, but once you combine read and write, you realize that they are not 100% orthogonal to each other, and they have side effects. So we have continued to develop our Disk Explorer tool. This shows diagrams from version 3 of the tool, measuring the disks on AWS i3 instances. And this shows essentially 3 dimensions. The x-axis shows the write bandwidth that we send to the disk. The y-axis is read IOPS, how much we load the disk for reads. And the color code is the perceived latency, how long it takes to satisfy the reads. So we can see that if we send only pure reads, we get very good read throughput in low latency. And when we send only writes, we also get good write throughput in low latency. But once we combine, reads badly affect writes and vice versa. So the goal of the IO scheduler is to limit the read and write concurrency, how many reads and writes we send in parallel, so to be able to stay in the blue area of the graph.
Benny, can I ask a quick question from my side?
Of course.
When do Scylla run the Disk Explorer? Is that something that run all the time on the background, or is that something that is pre-calculated?
Okay, so this floor is first run in the lab. So to calibrate the known disk models that we support in the cloud. So when Scylla is installed on a known cloud instance, it already benefits from this calibration process. If a user wants to install Scylla themselves, they can also run it at their own time and feed the report from this explorer to the Scylla setup script that writes this in Scylla's configuration, which is used every time Scylla starts. But it is not something that we run in the background continuously.
Thanks.
Right. So to the next slide. For this model to be practical, we actually do a linear regression and model the disk performance model by a straight line under which we would like to stay, showing that the sum of ratios on the upper right is bound by a constant. So to sum up the requirements for the I/O scheduler, so we first need to collect the information about the disk so we can build an algebraic model of the disk performance behavior. We use that to build this model, and we embody the model into the I/O scheduler in real time. So to show the effect of the new scheduler, we can see here the write and read P99 latencies while replacing a node in the cluster. So node replacement causes a lot of I/O for the administration process. We read existing, basically scan the whole database and reconstruct the data on the replacement node. And we would like to serve regular queries in the foreground without them being affected by the maintenance process that runs in the background. So on the left side, we can see the results for version 4.6, which had the old I/O scheduler. And we see that the write latency, P99 latency is pretty high. It's close to 70 some milliseconds. Read latency is better, but still it's much higher than 10 milliseconds, which we usually consider as the upper limit we would like to stay under. And in version 5 and in master, that when this slide was drawn, it was 5.1. We can see that the P99 latencies stay very low, under 10 milliseconds, even while replacing a node in the cluster. So how does this look over the Grafana monitor? This is with 4.6, and we see at the bottom, we see at the bottom that the P99 latency is pretty erratic, and it's very high. It's hovering around 80 milliseconds and sometimes over 100 milliseconds. While with 5.1, latency behaves much better, and most of the time stays below, well below 10 milliseconds. Thank you very much, and I'll pass the microphone back to Tzach.
Thanks, Benny. Before I switch to the next topic, I want to quickly answer a question from the Q&A. So there is a question: is Scylla optimized for large reader writes or smaller? What is application? Is a sweet spot, I would say, of Scylla. So I would say that the sweet spot of Scylla is anything that combines big data and a real-time query. So Benny will later touch on the difference between what we call OLTP and OLAP. Scylla can support both, but I would say that if you don't have any real-time aspect to your application, maybe you don't need Scylla. Scylla is excel in real-time application where latency is critical. So I can give you a lot of examples like IoT or EdTech or things like that. Every time you build an application and it's important for you to get a sub-millisecond response or a sub-10 millisecond response, then Scylla might be the answer for you. If you don't talk in the millisecond, you talk in hours or something like that, maybe you can use a data lake or something like that. So I hope that answers the question, and if not, we can get back to that.
Tzach, if I may add, just from the IO scheduler perspective, I can say that we actually optimized for both, or we take into account both the IO kind and the IO size. So when we basically estimate the amount of resources that are consumed by a particular IO, we look whether it's a read and write, and we also look at the IO size. So we basically try to optimize between IOPS and bandwidth. So for example, compaction is doing reads in large buffers. It could read like megabytes of data sequentially, while SQL queries may do random IOs, for example, when reading the index, and these are 4K IOs. So essentially, we would admit more random IOs versus a single large read for compaction. So the answer is both.
Thanks, Benny. Okay, so a lot of our users, both on Scylla Cloud and Scylla Open Source Enterprise, run on AWS and EC2. Until recently, our go-to instance type was the i3 and i3EN family. Recently, EC2 started offering a new instance, i4i, and we actually got a preview of it before it was officially released. Because AWS know that we are into high performance and speed, and we are very pleasantly surprised from the performance of this new instance, and I thought to share some of our results. So this is the Disk Explorer that Benny talked about earlier. You can already see just from the shape and color of the results that the range in which this new storage perform is much better than the older one, and almost all the combination of bandwidth and requests per second that we try work better than a previous generation of instances. Translating it to throughput and latency per instance, we found out that the throughput is actually more than twice than what we used to have in i3, and the latency is actually lower. So a big win for Scylla and for EC2 in that case. And if we stretch this result and we actually tested it on a 3-node cluster, you can see that the 3-node cluster, by the way, with replication factor of 3. So each of the node in this case hold all the information, and the cluster can support way over 1 million requests per second with the low latency. Those of you with some experience with database, you can appreciate it's a pretty high number for such a low cluster. And as you can remember, Scylla can actually grow and grow in the number of nodes. It can actually grow to 100, 200 nodes in a cluster. You don't often need that because each node is super powerful, as you can see here. But on some cases, our customers do grow to 70 nodes. For example, if you want to distribute over a lot of regions, or any other reason. So well done AWS, and Scylla work very nicely on these instances. And with that, let me switch back to Benny to talk about the latest benchmark he executed.
Hi again. In this benchmark, we wanted to measure the performance of a very large cluster of Scylla that holds about a petabyte of user data, uncompressed.
Benny, I just want to mention one thing. This benchmark was done before we had access to i4. So this is still on the i3, and you can maybe try to translate it to i4 numbers after.
All right. Okay, so to start, just let's go over the bill of materials quickly. So the cluster was comprised of 20 instances of i3en.meta, each having almost 100 cores, 768 gigabytes of memory, 60 terabyte of NVMe disks, and 100 gigabit per second networking. And in order to present enough load to saturate the cluster, we needed 50 load generators of the kind described here. One important thing to note here is that this HTOP screen capture shows that we were able to saturate all cores in the system. But an interesting point is that you see that on the upper row, those 4 cores are doing only kernel work, while the other cores are doing both user CPU and kernel CPU. And the reason to that is that on very large machines that have a non-uniform I/O architecture, we need to reserve cores for interrupt handling. So those 4 cores at the top are only handling IRQs, while the other cores are handling the regular Scylla stack that's doing most of the work in user space and are also doing some system calls to get to the kernel. So to start with, we wanted to see how much load we can reasonably put on this cluster while serving the IOs in reasonable latency. So we started with 4 million IOPS, and the mix is that most of them are reads, 98% reads and 2% writes in a Gaussian distribution. And we see that even with this quite high bandwidth, the P99 latency is under 2 milliseconds for writes and close to 1 millisecond for reads. And only when we kept increasing the throughput up to 7 million I operations per second aggregate on the right hand, write latency, P99 latency started to rise and got over 6 milliseconds, while the read latency, P99 read latency is still fairly low, only at 2 and some milliseconds. The actual workload that we wanted to benchmark consisted of 2 simulated applications that ran in parallel. So the chunkier, the heavier application produced 5 million I operations in 80-20 ratio, 80% reads and 20% writes over the bulk of the data. This simulated a user analytics application. So, for example, it could scan user profiles and look for patterns in those profiles. And on top of that workload, we had the main application workload that worked on a much smaller data set. and produced 200,000 IOs per second in a 50-50 ratio, 50% reads and 50% writes. And this simulated an OLTP application. For example, it could be like a bidding application that uses the analyzed data in order to compete over a bid for, say, an advertisement placement. So what we can see here is that the main application doing the 200,000 IOPS had a P99 write latency of about 2.5 milliseconds and the read latency of 4.5 milliseconds, while the user workload of the 5 million IOPS had much better write latency of 1.25 milliseconds and the read latency of 3.7 millisecond. So essentially, it kind of won the tug of war between these two applications. But unfortunately, the requirements for these applications are completely different. The analytics workload is not that latency sensitive. It needs the throughput, but it doesn't care if each request is served much slower because it reads in large batches and it's doing much fewer writes. On the other hand, the bidding application needs the best latency it could get. So here, what comes to the rescue is a feature that we call workload prioritization. That is shown here, the race between the heavy traffic on the left doing analytics versus the race car that needs the lowest latency. And if you remember the diagram showing the scheduling groups with shares, we can use the same mechanism to separate the number of shares we give to each query of the OLAP category versus the OLTP category. Now, with that applied, what we can see is that when we apply workload prioritization, we were able to reduce the bidding application latency, write latency, down from 2.5 milliseconds to 1.2 millisecond, and the read latency from 4.5 milliseconds under 4 milliseconds to 3.7. And on the expense of the user workload, where it still have reasonable latencies, but much higher than before. So our P99 write latency went up from 125 to 325, and read P99 latency from 3.7 to 6.5 milliseconds. But goal achieved, and that's the most important thing. We can show here the graphs for the two workloads. So on the top, this is the application workload that gets a smooth bandwidth of between 1 to 1.5 megabytes per second per shard, while the user workload is getting steady, little under 30 megabytes per second per shard in the system. So, thank you, and back to Tzaf.
Thanks, Benny. So we don't have much time. So I will quickly present a few performance improvement that we just recently or relatively recently did in Scylla 5.0, which is out for a few months. One of them is related to wide partition. So first I need to explain what is I already talked about partition, but what is a wide partition? So as I mentioned in Scylla and other NoSQL database, we partition all the data between all the nodes, and in Scylla we also partition it between the cores. And that's go for the data modeling as well. All the rows in a table, and Scylla have a table similar, I guess, to a relational database. All the rows split into partition. So one partition can actually have a lot of rows. In this example, we have something like an IoT medical application, if you will, when we track the heart rate of your pet heart or your own heart. So each partition can be a person, and each row in the partition have a timestamp as what we call a clustering key or ordering key in DynamoDB term, and a value, the heart rate. So as you can see, all the result for one person is in one partition, and this partition is in one node or three nodes with replica. This allows to very quickly, or allows Scylla to very quickly query information about one person. So if you query, for example, the last heartbeat of a person, or the last 20 heartbeat, or all the heart rate of a person per day, the result retrieve very, very fast because it's only need to query one node. But the result of that one partition can grow to millions and even billions of rows per one partition. This used to be a problem in earlier version of Scylla, and it is a problem in other database without mentioning name. We did a lot of work to eliminate this issue, and I'm happy to say that in recent version of Scylla, this is not a problem at all, and it's a valid data modeling. The last hurdle that we need to remove to have this work smoothly is moving the indexes of each partition, which was purely on RAM, to be adaptive. So part of it are on RAM, part of it are on disk, and the decision what to put where is actually based on read patterns. So if an index is read more often, it will be in memory. And basically now you are free to use as large partition as you will when you create a data modeling. You still need to keep in mind that if you have what is called hot partition, meaning that a lot of requests are coming to the same node and the same core, you probably have a data modeling issue, because then this core will be overloaded while the other nodes or core in the cluster will be not utilized. So if you're using our monitoring stack, you actually have a small window called a Scylla Advisor that will start beeping in red if you create such a bad data modeling. Another thing that we optimize in Scylla 5.0 is reverse query, when you query the data in a reverse order. So I mentioned earlier that all the rows in a partition are ordered based on a clustering key, but what if you try to read them in the reverse order? Sometimes you want to do that. So this was a suboptimal performance, and now it is fixed. You can actually query in both directions, and it's work pretty similar. Another thing that I do want to mention, that we also implemented a new driver in Rust. Drivers, any database driver, of course, any application driver is also part of the end-to-end performance that you get from a database, and we're investing in this aspect as well. The Rust driver also use some of the technique that we learn on the database itself, like completely asynchronic and other implementation, but that's a whole new topic. Maybe we'll have another session just about the Rust driver and optimization we did on the driver side. So I want to conclude with mentioning that performance is a huge topic, and as people ask, and Benny says, it's performance can be split into read and write, big chunk and small chunk, analytics and real time, throughput and latency, and each of them it can be measured differently and optimized differently. I would say two things. One, that higher throughput can be easier to understand and very easily converted to cost, because if you have higher throughput, for example, million requests per second on one node, that can be quickly translated to just using less nodes on the cloud, and of course, that can very quickly reduce your cost. Reducing latency does not necessarily translate to cost, but can be very directly translated to revenue. Because if you're talking about a gaming application or a BDAT application or anything that requires fast response, low latency is critical to you. And low latency is something that you can actually not fix by throwing money at the problem. So if you have a database or an application with high latency, it doesn't matter how many instances of this application you will put, all of them will have high latency. So it's harder to fix, and this is why we're working on it for the last 8 years. And with that, let me launch or ask Cody to launch the last poll. How much data you have under the management on your current database? Thanks, and now we can move to the Q&A section. By the way, a question to the audience. How many people use Scylla right now? You can raise your hand. I cannot really see you, so better if you can answer on the chat, it will be more useful. Okay, so I'm starting to see questions. So the first question, how big can a Scylla cluster be? So there is a theoretical and practical aspect of it. So theoretical or under QA, we tested, I think, 1,000 servers. Practically, because each server of Scylla is so powerful, our largest production cluster, or our customer production cluster that we know of is around 100 machines. And the big number of the machine is usually for high global distribution. So people who have a cluster can stretch in the entire globe. So some cluster in North America, some in Europe, some on Asia, etc. And all of them are in sync. And this is how you get to a large number of machines. Okay, looking for more questions. Okay, a question about drivers. I mentioned earlier, I think I mentioned that Scylla is compatible with both Apache Cassandra and DynamoDB. And the question is, can I use Apache Cassandra driver to work with Scylla? So the answer is yes, but you can do better. So yes, because the protocol is binary compatible, any driver that work either with Cassandra or with Scylla, either with Cassandra or Dynamo will just work with Scylla as well. But we fork the driver or implement even our own driver from scratch in some cases to get even better performance, both from the driver and the database. So my answer is, if you can put your hand on a Scylla driver, you better use that. If you cannot, because we didn't implement such a driver, for example, we didn't implement a JavaScript driver yet, then you can just use the Apache Cassandra driver. It's absolutely compatible. Okay, let's wait for a few seconds for more questions. And if no more question, we can conclude.
So while we give our audience this chance to send in any more questions, how about I go ahead and give away a couple of gift cards? So these are for 4 $25 Amazon gift cards. Our first winner is Brian N. Our second winner is Manu S. Third winner is John P. Our fourth and final winner is Jack K. So to our 4 winners, congratulations. Please keep an eye on your inbox to claim those gift cards. But if you do not see an email, just check your spam folder. And I'll also take this opportunity to remind everyone that this session was recorded. Following this program, you'll receive an email with a link to access the recording, or you can find it living on the DevOps website at devops.com/webinars. All right, Zach, are you seeing any more questions coming in?
No. I hope we answer all the question, or people got bored, or both. but also I want to mention that if you do have a question, you can always jump on the Scylla Slack. It's very active. Scylla developers, Scylla users are all hanging out on the Slack channel. So you can join and ask questions there if you're too shy to ask them now.
And of course, I think people are always invited to take Scylla Cloud for a spin and launch a sandbox to play with.
Well, all right, Zach and Benny, I thank you so much for joining us today and sharing your expertise with us. If you'd like to follow ScyllaDB, there's socials right there on the screen, so go ahead and take a look at those now. So to ScyllaDB, thank you so much for sponsoring today's program. And to our audience today, we really appreciate you spending time with us as well. We do ask for one extra moment of your time to fill out a brief survey that will pop up on your screen as soon as we conclude. Zach, you got something?
Just thank you very much for having us, Cody.
Of course. Thank you both for joining us. And to everyone, have a great rest of your day. We hope to see you at an upcoming TechStrong Learning program.